There's a group of people now at CERN looking at what applications of quantum computing could be applied to high-energy physics. It's quite a rich area already. There's a couple of big roadmap documents were published last year.
In 1981, Richard Feynman gave a keynote that proposed simulating physics with computers. We've come a long way with the resulting quantum computers, and you might have heard about business use cases for them. But how much progress has been made in using the machines to understand the universe? Who better to ask than Dr. Harry Cliff from the LHCb experiment? He discusses how quantum computers can simulate particle interactions or handle the mind-boggling amounts of data generated at CERN. We also dive into his new book, Space Oddities, in this episode of the Post-Quantum World. I'm your host, Konstantinos Karagiannis. I lead quantum computing services at Protiviti, where we're helping companies prepare for the benefits and threats of this exploding field. I hope you'll join each episode as we explore the technology and business impacts of this post-quantum era. Our guest today is a particle physicist at the University of Cambridge working on the LHCb experiment. He's the author of two wonderful science books, How to Make an Apple Pie from Scratch and the fresh off the press Space Oddities. Harry Cliff, welcome to the show.
Great to be here. Nice to meet you, Konstantinos.
Yeah, thanks. I have to confess, I'm a fan. Thrilled to have you on here. Your publisher sent me an early copy of Space Oddities, and it was just as readable and engaging as your first book. We'll dive into ideas from those books in a moment, but I'd love to orient listeners kind of high level and explain your work a bit. So most people have heard of the LHC, but can you give a brief overview of what that machine is and explain why there's a tiny little B appended to LHCb?
Yeah, sure. Well, so the LHC, it's the biggest scientific instrument that's ever been built. It's just outside Geneva on the border between France and Switzerland, about 100 meters underground. It's essentially a 27-kilometer circumference ring, and its job is to study what the universe is made from. That's ultimately the really big question that we're all working on in one way or another at CERN. And what it does, we're trying to figure out what the physical world is made from, and we do pretty much the simplest and most brutal thing you can imagine, which is to take little bits of the world in the form of protons, which are subatomic particles. You accelerate them around this ring until they're going 99 with 9 sixes after it % of the speed of light, and then you crash them into each other and you see what happens. And my experiment is one of 4 big detectors that are spaced around this ring. And essentially what it is a big 3-dimensional digital camera the size of an office building that records what happens in these collisions. And then in those collisions, you're looking for, lots of different physicists are looking for different things. I'm particularly interested in particles called beauty quarks, which is what the B in the name of my experiment stands for. So LHCb, Large Hadron Collider Beauty Experiment. And these beauty quarks are very interesting because the way they behave, the way they decay, the way they interact with other particles can tell you about the fundamental forces and the fundamental interactions that exist at very, very short distances when you zoom right down smaller than an atom. So that's the sort of very big picture of what we're doing and what the LHC is.
And it's been generating news for a while, the LHCb especially. Do you want to talk a little bit, before we step away from that, do you want to talk a little bit about the fifth force of nature and this potential mystery that we might be solving?
Yeah, so the book Space Oddities that I've just finished working on is about anomalies. So it's about and what an anomaly really is in science is a result that you didn't expect. So it's some place where you observe something in the heavens or you see something in your lab that you can't really explain, that sticks out from your expectations. And there are a bunch of these anomalies. At any one time, there's a bunch of anomalies in circulation, but there's been a set of anomalies in the behavior of these beauty quarks for emerging over the last decade or so. So actually not just at the LHC. So we've seen these beauty particles behaving in ways that you can't explain with our prevailing theory of particle physics. So we've seen some anomalies at LHCb. There have also been hints of anomalies at other experiments. There's an experiment in Japan called Bell, and there's one in California, now defunct, but they're still analyzing the data, called Babar. And so you have basically, in essence, what has been seen is that these particles are decaying when these beauty particles are created, they live for a very short period of time. So they live about 1.5 trillionths of a second. and then they decay, so they turn into other particles. And there's lots of different ways that they can decay. And our theory, which is called the Standard Model, can be used to quite accurately predict how often different decay should happen, or in a certain decay, what angles the particles should go out at, or how much energy they should have. And through a range of different measurements, there are a whole set of these decays that don't quite line up with what you'd expect from the theory. And what's been quite exciting in the last decade or so is that theorists have found that you can explain all these different anomalies at the same time if there is a new force of nature, so a fifth fundamental force beyond the four that we already know about. So it's potentially a clue to what would be a really big breakthrough in fundamental physics. The problem with these anomalies is that the experiments are very, very complicated. So there is always a possibility that some of them could be explained by an experimental glitch or a missed effect that you didn't account for. And in fact, some of the anomalies have recently disappeared for that very reason. There's also sometimes, strangely, it might sound strange, but sometimes actually it's quite difficult to calculate from your theory what you should expect, because the theory is very complicated and the interactions are very complicated. So it's an unresolved story at the moment. We have these clues, and we don't really yet know whether they are really evidence of something exciting and new, or whether it's something we've misunderstood in our experiment or our theory. But we're working very hard to try and figure that out.
Yeah, you did a great job in both books talking about this idea of minimizing the uncertainty of or error, right? And when you get down to it, I mean, we're not going to go deep into the statistics of it, but this idea of you want to be able to get down to, let's say, 5 sigma to show that it's significant, right? A million, like a 1 in a million chance or something that you're wrong. So do you want to talk a little bit about the headaches involved with that? Because there's a theme here, right? Like dealing with data and then where we're going to with quantum computing and everything. So if you just want to talk a little bit about how challenging that is.
Yeah, I mean, okay, so maybe I should explain the 5 sigma thing for people who may not have come across this. But I mean, in particle physics, this standard has emerged at which point you can kind of say you've made a discovery, and it's called 5 sigma. What it really means is that if you have a set of data and you have a prediction from your standard theory, the data has to essentially move away from the theory by 5 standard deviations, so 5 units of uncertainty. So let's say you're measuring some property of a particle, say its mass or its magnetism or something like that. That number would have to be 5 errors away from the prediction before you can say this is a bona fide discovery. And the reason for that essentially is that in an experiment experiment like the LHC, you have trillions and trillions of collisions that are analyzed by thousands of people in different ways. And in fact, you make thousands of measurements, actually. So there are well over 1,000 papers that have been published using LHC data. That is a bit of a problem because if you have 1,000 experiments, just by statistical uncertainty, you will get some measurements that randomly will wobble away from your data by quite a large amount. It's a bit like if I gave you a coin, say, and I said, I want you to tell me if this coin is fair. Let's say you toss that coin, 10 times, and you got 10 heads in a row. Now, that's very unlikely. That's a very unlikely thing to happen. And you might conclude the coin is biased. But if I actually told you that I gave that same coin to 1,000 people, and you were the only one who got 10 heads in a row, you would go, okay, maybe this is just luck. I was 1 in 1,000 lucky person who got this result. So the reason you have 5 sigma is at that point, when it's 5 errors away, the chances of a measurement wobbling away from the theory by that amount is less than 1 in a million. And we don't do millions of experiments. So that means it's very likely to be real. But that's just statistical uncertainty. So that's just kind of this random wobble that you get in like a coin toss or a dice roll. But there's also other kinds of problems like what we call systematic biases that are effects in your experiment that you haven't properly accounted for. Like, a good example of this would be, this is exactly what happened in an experiment that I work on. We were comparing how often these beauty quarks decay into 2 different types of particles. So we were comparing how often they decay into particles called electrons, which are probably familiar to your listeners. They're the things that go around atoms. And then another particle called a muon, which is basically the same as an electron. It's just a bit heavier. So there's basically 2 very similar particles. And you expect the decay to electrons and the decay to muons to happen at the same rate. The problem is that the detector that we have is much better at seeing muons than electrons. So muons are really easy. They kind of go through the whole detector. They leave a big electrical signal, no problem. Electrons, they kind of scatter and they're messy and they're easy to confuse with other particles. So when you make your measurement, you can't just count how many electrons and how many muons you see, because you'll end up, what you're actually seeing, you'll see a difference, but the difference is due to your detector not being perfect. And you have to account for that. And if you get that wrong, then you can get a biased result. And so it's actually that I suppose the biggest job of any experimental scientist is chasing down those systematic biases, because these detectors that we work on, they have millions of sensors. They've been incredibly complex devices. The way that particles interact with them is very complicated and actually not totally understood from a theoretical point of view, where you can't simulate it perfectly. So you have to use a combination of simulation, data-driven techniques, physical intuition to try and unfold all these kinds of biases before you can actually then finally make your measurement. And that is a very long process. I mean, people are often surprised, I think, like how long it takes us to produce scientific papers. I mean, I think papers can take years and years. I think the result I worked on most recently, I started working on in 2015, and it wasn't published until 2021. So there's a very long time developing these results, because you have to take into account all of these different effects before you could say with confidence that you've measured something properly.
That's certainly longer than any quantum computing paper I've worked on. although I can relate to the errors. I mean, we see that the machines are prone to errors, and we have to account for that, and we have to do multiple shots and then compare what the most likely answer was, and all these worlds converge. And you were there since 2008 when the machine switched on, right? Like that's basically when you got started. Right. And you were involved, I guess, in the early days with doing some code, and ever since then working with data. So you're no stranger to all the mass amounts of data. So if I can get your thoughts on what it's like dealing with that much data, and we're going to, of course, now turn attention in a moment to quantum computing. It's a lot, right? Like you couldn't even capture everything that comes out of the LHC, right?
Yeah, no, that is true. I mean, this is probably a bit out of date, but I remember doing some research for a talk I was giving at a data science conference. This was almost a decade ago now, but I kind of worked out how much data the LHC produces each year, actually produces. So not what we record, but what comes out of the detectors every year. Mm-hmm. And I think it was something like, if you recorded all the data the LHC produced in a year, it would exceed by orders of magnitude all the data that's ever been produced by the human race or ever recorded by the human race, including like all internet traffic, all telephone conversations. So it's a vast flood of data. And so yeah, it's a big challenge. I mean, the first thing that has to happen is where you cannot record it. It's just not possible. So in real time on the experiments, there is a decision-making algorithm called a trigger that basically says, it looks at each collision as it happens and goes, is this interesting? Is it likely that something interesting has happened in this collision? And if it thinks it's interesting, it will record it or pass it to the next level of decision making. But usually, most of the time, it's just thrown away immediately. So we only keep about 1 in 100,000 collisions or so. And you've got, just to give you a sense, you've got 40 million collisions, interactions every second in all 4 detectors. And that happens 24 hours a day, 7 days a week, about 9 months of the year, with a few little breaks in between. So that gives you a sense of the vast amount of data. So I mean, that's one immediate challenge. And I suppose one of the scary things about these triggers is you design them to record things you hope or expect to see. But there's always a chance that, well, A, you just code it wrong and you lose the signal you're after because it gets thrown in the bin and it's lost forever. Or there are things you didn't expect. So there could be that there's some exciting new signature that we just never thought of, and our triggers aren't designed to recognize it. So that's one challenge. But I mean, I suppose practically from my point of view, as we've accumulated more and more data, one of the really big challenges is the time it takes to process it. So if you want to sort of change the way you're processing your data or analyzing it, running back over the entire data set can take months now because the data sizes are so huge. The other really big challenge, and I think this is maybe where quantum computing will come in the future, is in simulation. So the way I talked about unfolding these biases from the data, one of the main tools we have for this is large quantities of simulated data, where we simulate the entire experiment from the kind of quantum mechanical interactions of the protons in the collision all the way through how the particles interact with each sensor in the detector. So at the end of it, what you get out is data that looks exactly, well, as close as we can, that it came out of the real experiments. You simulate all the sensors in the detector, the electrical signals, how they're processed, and the simulation is put through the same chain as the real data. And it's pretty good. I mean, it gets pretty close to what the real data looks like, although there are some areas where we know it doesn't really work, doesn't quite get things right. But as you have larger and larger data sets, you've got to deal with these systematic biases to a greater and greater level of precision. And that means more and more simulation. So then it's how do you get the processing power to generate that simulation, because it's very CPU intensive, and then storage is the other problem. So this is increasingly the sort of thing we run up against, actually. It's not so much we don't run against like experimental hardware problems, it's computing problems that are really like the biggest challenge, particularly as we're now moving into an era where the LHC is going to get upgraded and record data at orders of magnitude faster rates than it has in the past. So this is only going to get worse as we go forward.
Yeah, I know you have that whole blend of time where you have to spend some time actually getting results and sometimes improving the machine, right? It's like a trade-off that happens. So a few thoughts on what you said. This idea of trigger, they sound a little bit like classifiers, like in information. Like if you're looking for fraud or whatever, you would run like classifiers. And there is always the risk that you don't fine tune it and throw things out. So I would hope that maybe one day, maybe even quantum can help with that initial trigger classification and do a better job of that gray area, that granular line, and where it is. But then dealing with all the information you actually get. Feynman, when he came up with the idea for quantum computing, he was thinking along the lines of exactly what you said, simulating reality. It is a quantum reality. And in some ways, you're going to run out of resources the minute you try it. You mentioned how many particle collisions there are, and just where those particles can go. So I would think that that's a natural fit. So it's been frustrating to me over the years that so few scientists even gave a thought to using a quantum computer one day to do that level of it, just because it's kind of where it all began. So are there folks right now at CERN like giving thought to following the path of like quantum development and seeing how that simulation could go on?
Yeah, there absolutely is. There's a group of people now at CERN working on kind of looking at what applications of quantum computing could be applied to high energy physics. It's quite a rich area already. There's a couple of big roadmap documents were published last year. Actually, I was mugging up on them as preparation partly for this podcast. I think the thing that seems really interesting from my point of view is one of the biggest challenges we face at the LHC is to do with the fact that we're colliding protons. So protons are not fundamental particles. They're made of particles called quarks and gluons. You can think of a proton as like a kind of messy bag of particles. And when you smash them together, those quarks and gluons interact in a really complicated way, and then stuff comes out. And the particles that come out are also not fundamental. They're usually other particles made of quarks and gluons. And the theory of quarks and gluons, which is called quantum chromodynamics, Feynman helped to develop back in the 60s and 70s, actually. The problem throughout its history is it's very difficult to do any calculations with, because in a lot of the regimes you want to apply it, it's a non-linear theory. It's got strongly interacting theory, so you can't use the traditional techniques which we use in quantum mechanics, which is called perturbation theory, where you essentially break your interaction up into a series of terms that get smaller and smaller, and then you can ignore the small ones and just basically calculate the sort of leading order terms. That doesn't work in quantum chromodynamics. And the solutions we have at the moment are incredibly CPU intensive. They basically involve breaking space-time into a lattice and solving it at particular points in space-time, and then you have to put it through a massive supercomputer. And long story short, basically, some of the biggest challenges we have of extracting physics information from our data is we don't understand how quarks and gluons behave. And one of the interesting applications of quantum computing could be new ways of simulating the theory of quarks and gluons. So you can actually get a much more accurate and also much more efficient calculation of the properties of these particles. And if you could do that, that would really be revolutionary, because it would allow you to access what we're really interested in is not these messy things made of quarks and gluons. We're interested in the fundamental interaction that happened, right in the center of the collision, and that will allow us to unfold that from the data. So I think that is very exciting, and particularly even my own work on these anomalies. some of these anomalies, one of the problems with them is that we don't really understand the theoretical prediction because it involves quarks and gluons, which you can't calculate very easily. So anything that helps us with that will make a big difference. Of course, there's also, I think, as you say, on the experimental side, it could well be that, I'm not an expert, but I think people are looking into the use of, quantum computing for classification, but also for reconstruction of the data. So there's this step before you get to analyze the data where what the actual data looks like is you've got this detector with millions of sensors, and what you have is hits in the detector. So there were hits here in these sensors with this much energy deposited or this much light in this detector. And that sort of unprocessed information has to be turned into, well, these series of flashes of electrical energy or actually a particle going in this direction with this momentum, and you fit a sort of track through those dots in your detector essentially. And so there's also people looking into the use of quantum computing to speed up that process, where you, rather than using kind of classical algorithms to do this, you could potentially do this more quickly using quantum algorithms. But I think it's still an early stage, I think, of development, this kind of work. But they are looking, as I understand it, at near-term noisy quantum computers of the type that are available or going to be available in the next few years, rather than waiting for, sort of much larger scale quantum computers where you don't have to worry about noise in the same way. So I think there's people are trying to do this.
You just have to run it a lot of times, lots of shots, like we said. And you guys are used to that. I think you run things, as you said, all day. The reason the LHC is buried so deep is, can you imagine what the neighbors would be listening to if it wasn't? I mean, a racket 24 hours a day would be too much.
Well, it's very quiet because it's in a vacuum. So you're right. I mean, I know. Actually, interesting. The reason it's underground is actually quite interesting. People often assume that it's because it's radioactive or dangerous, but it's actually just that it would have been incredibly expensive to buy 27 kilometers of land to do this. So you'd have to knock down people's houses and build over farms. So that's why essentially it's underground. Underground, no one, kind of has anything going on once you're below 100 meters. So, yeah.
The not in my backyard argument becomes not under me, but yeah. Yes. And there's a wonderful elegance, this idea that quantum computing, which we are able to do because of our understanding of quantum physics, might yield a new understanding of quantum physics in the end. That I just love that. There's something wonderful and cyclical about that, like the LHC, something very cyclical. And there's other stuff going on at CERN too that might feed into quantum computing, right? There's cryogenic research, other things like that. You might find new ways to improve devices there that can feed out. So there are papers being published, I'd imagine, also just on those more technical aspects besides what particles are discovered or things like that.
Yeah, I mean, I think I don't actually know to what extent CERN is developing actual quantum hardware. I mean, it certainly has got a lot of expertise in cryogenics. I mean, the LHC is the biggest cryogenic facility in the world, but it's quite specifically for cooling superconducting magnets down. One of the growth areas, which is sort of adjacent to one adjacent area is quantum sensing. So using quantum sensors in cosmology experiments. So there's a project that a few of my colleagues are involved in at Cambridge, which is this, it's a gravitational wave detector that uses atom interferometry. So this is essentially using entangled atoms that get sent down two different paths of an interferometer, and you can use this to detect dark matter gravitational waves from the early universe. And this is all based on quantum sensing. So there's a collaboration going on between high energy physics and very, very cold physics, which are very low temperature physics, which traditionally have been sort of quite distinct areas, but they're coming together to build these new sorts of instruments, which is sort of it's quantum, not quite in the way, not in the same sense of quantum computing. But that, I mean, quantum sensing is another big area that I think is going to have huge impacts in the future.
We've covered it a few times because it does have real world uses already. It's amazing, and one day there'll be a new detector for gravitational waves buried in yet another bayou somewhere, I'm sure, where they'll be detecting these kinds of things. That's a very specific reference. You have to read the books to get that, but it's a very so your writings, I mean, really clear and remarkable. You have a way of explaining these complex topics clearly, and you bring readers places they couldn't physically go. So in Space Oddities, in just a few paragraphs, you you bring us to like the beginning, the big bang, and then inflation after. I just thought it was really well done. And then I remember in Apple Pie, you you brought us into the mind, or pseudo mind of the protons that are about to be smashed together, and how they would have been immortal otherwise, and all that. I don't know. That was just incredible. So when you think of these visual ways of getting across information as a science communicator, what's your process like? Is it something like exploring the daydreaming of thought experiments? Is it some similar place that you go, like a liminal world where you conjure this?
It's a good question. I think sometimes these ideas just sort of come to you. I mean, actually, that passage you're describing from the first book about essentially what I describe for people who haven't read the book is the first collision at the LHC from the point of view of the protons. And that actually kind of came from a project I'd worked on many years before, where I used to work at the Science Museum in London, which is the UK's national science museum. And we did an exhibition about the Large Hadron Collider, and I was one of the curators of that show. And we spent a lot of time discussing with artists and designers about how we should structure the exhibition, because we kind of decided we wanted to take people on a trip to CERN. One of the ideas that emerged was, well, maybe as a visitor, you're the proton. So you basically follow the rig of the LHC from the proton's point of view. In the end, we didn't go down that route because we thought it'd be too weird. But that idea was sort of lingering in the back of my head and somehow just came out when I was writing. But I mean, I think in terms of, I have quite a visual imagination. So when I'm solving problems in physics, particularly, I mean, both in my research, but also when I was, say, an undergraduate solving algebraic problems, usually it was about coming up with a mental picture and a sort of intuition for what was happening that allowed me to solve the problem. It sort of starts that way, and then you have to sort of codify it in mathematics. So I think that's the way I've always thought, and I think that's where these sort of, where some of the imagery in the books comes from. But another big aspect of it is I try to get across not just the sort of the abstract physics, but also what is it like being in a scientific workplace? So some of these, some of the places that people work are really extraordinary. Astronomical observatories on mountaintops. It's they're incredibly well. If you don't have to be there, 30 nights in a row on a cold evenings, it's an incredibly romantic place. If you're just visiting for a night to sort of like write a story down. I think these are sort of spaces that most people don't get to experience. Very relative few people get to go to CERN and go underground and see the LHC. So I do try to get some of the kind of magic and excitement of these places across in the writing as well. So I guess it's a mixture of that kind of what's it like as a scientist versus also trying to find ways of visualizing what's going on. Quite often the physics itself is really abstract, and it's difficult to kind of get your head around unless you can come up with a clear mental picture of what's happening.
Yeah, I got to spend some time at Fermilab. I was there because of the qubit work they're doing, which is kind of like a qubit, but more dimensional states. And when I read your description, I was like, oh, yeah, he totally nailed it. That's exactly what it's like there. So that was it. Yeah. So, you definitely have that ability. When it comes to that like thought experiment idea, you also work in the actual experimentation too. So you kind of bridge those worlds, right? It's not just like dreaming up things like Einstein riding on a beam of light or something. You're actually like down in the trenches too at the same time. So just any thoughts you have on the importance of those two worlds coming together, the practical experimentation and the theoretical?
Yeah, I mean, they are, theory and experiment have to work together. So I mean that they're two sides of science. Without one can't function without the other. I think that in a way it seems to me that the days of people like Einstein sitting there in his patent office imagining what it's like sitting on a photon and coming up with deep truths about the universe, I think there was this particular period in the 20th century where that kind of thinking worked. But I think a lot of now the theoretical problems are much more difficult, and it's very hard to make progress because so much of the sort of low-hanging fruit has already been plucked. So I mean, a lot of theorists, I think, now work much more closely alongside experiments. So they're kind of listening to what their experimental colleagues are telling them and then coming up with ideas that then feed back to us as experimentalists, saying, well, have you tried looking for this particular signature or in this particular place or building this kind of experiment? So the two are constantly interacting with each other. I mean, it's also interesting in particle physics, in high energy physics, where you're working on these huge projects that have thousands of people on them. There's a high degree now of specialization. So back in the mid 20th century, if you're an experimental physicist, you would have, designed, built, and analyzed the data from your experiment. And you might have done it in collaboration with 2 or 3 other people. Now, because these experiments are so vast, it's not possible for any one person to have a complete understanding of the whole thing. So you have a general overview, but my job, broadly speaking, is as a data analyst. So I essentially work on the data after all the hard work of building the experiment, making it run, processing it has been done. And people contribute in various different ways. And then you have people who are real experts on electronics, how to read data out from these detectors, or real experts on how to build photon detectors. And so actually it's now very highly specialized. So you have this kind of stratification. It's not just theory and experiment. You've got, hardware people, software people, data analysts, and even in between theory and experiment, you have this new discipline called phenomenology, which is sort of taking theory and using it to make precise predictions about what happens in an experiment. So it's phenomenologists actually that have the most to do with experimentalists. And then beyond that, you have the sort of high theory, I suppose, people who work on fundamental quantum field theory or string theory or whatever, that are several steps removed from the experimental world. But so I mean, I think the interaction of those two worlds is absolutely crucial. And I think that there is a sort of, I think, possibly dangerous idea that's got around in the last few years, this idea of post-empirical science. So there are people particularly who are working on quantum gravity, which is the sort of ultimate goal of fundamental physics, so sort of getting close to a complete description of the fundamental workings of the universe. One of the problems with quantum gravity is that there is precious little data on it, because the regimes in which the effects of quantum gravity become manifest are so extreme that they can't be created in the lab or any foreseeable lab that we might be able to build. So there's been this sort of suggestion, or maybe we can just assess a theory's validity based purely on sort of principles of elegance or self-consistency or mathematical beauty, and that's fine to an extent.
Slippery slope.
I think it's a slippery slope, and ultimately, to be science, you have to be able to say, is this actually what the real world is like? So I think, these two worlds have to work closely together.
Yeah, that really brings me to my next question perfectly. You set me up for it. So many folks in quantum computing tend to be fans of the many worlds interpretation. It's not a surprise, because the practical father of quantum computing after Feynman's idea would be David Deutsch. I mean, let's face it, he's the one that first came up with a way to get this machine to possibly work. So how do you feel about Everettian branching or other aspects of multiverses, including maybe the idea that we're in the right one for our fine-tuned numbers to be correct, and maybe in other ones it's not correct? It's like, do any of these ideas feel necessary to you? Like they're out there?
I mean, I'm kind of agnostic about interpretations of quantum mechanics. I think I'm not a theorist, so these are not things that I spend a lot of time worrying about or thinking about. I mean, I do think, quantum mechanics is deeply, there are deep mysteries about it. But I suppose the point at which I become interested in an interpretation of quantum mechanics is the point at which it says something about experimental physics that is different from some other interpretation. So whether you believe in many worlds or wave function collapse, it makes no difference in an experiment that we can conceive of, as far as I'm aware. So from that point of view, I think it doesn't really matter very much. If you get to the point where one of these theories is going to tell us something different about the universe, then fine. But I don't know. I don't really have. Idea. I think I don't think many. I think many worlds is a fun idea, but it seems like the idea of creating an infinite number of infinitely branching worlds just to understand why a wave function arrives at a particular point on a screen seems like a kind of, to me, a little bit of overkill. But I mean, as I said, I don't have a strong opinion about it. I mean, I suppose the anthropic argument, I've usually heard the anthropic argument applied not to quantum many worlds, but to other sorts of multiverse. So you have this thing called the inflationary multiverse in the early universe, which is where you have this exponential period of expansion before the Big Bang. And the Big Bang is essentially where part of this rapidly expanding space-time, the field that's driving this inflation decays and creates a spray of high energy particles, a kind of fireball, which is the Big Bang, and the expansion slows down in this little bubble. And the idea of inflation is that if this process is happening all the time, then you get bubbles forming throughout this expanding space, and you get multiple universes essentially. And in some versions of this, when a Big Bang happens, the laws of physics get set up differently. If you believe in string theory, it's because extra dimensions get squashed up in a different way each time. And you can then explain the fact we live in a universe that seems very nice and conducive to life based on the principle that, well, there are lots of uninhabitable universes, but we just live in the one where the conditions are right. I mean, I think my general attitude to multiverses, and I say this in the first book actually, is that I got on a bit of a rant, which is that the problem with the multiverse is it's a kind of get out of jail free card for any problem that you come across, particularly problems that are to do with fine-tuned fundamental constants or fine-tuned laws of nature that seem to be set up to create the universe that we live in, because you can just say, well, it was the multiverse. And it's not really a very helpful response, because it sort of shuts down the discussion. It says, well, there's not really a problem to solve here. It just happened that way by dumb luck, and we're here because that's what happened. And I think maybe that's true. Maybe there is a multiverse. Maybe it explains features of our universe. But I think we have to exhaust all the other explanations before we go to that point of view, because the problem ultimately with the multiverse is like many worlds interpretations of quantum mechanics, it's not testable. And so if you accept it, you're basically sort of taking something on belief or faith. And at that point, you may as well say, well, God set it up that way, or whoever your favorite deity is. So,
yeah.
Every
once in a while, I do see someone come up with something that feels almost testable. You'll read, like, over this past year, I've seen a couple of approaches where they're like, well, maybe if we see this, it'll prove some kind of multiverse. I don't know. I don't know if we're going to get to that. But you are potentially looking for a fifth force, right? You're looking for other anomalies. There's weirdness going on with like the Hubble tension. If you want to talk a little bit about that before we close out, and this potential crisis and all that, if you have anything to say there for listeners, it just gets the idea across that maybe something is detectable with a more refined machine in the future that would let us get a hint, just like gravitational waves or the cosmic microwave background. Maybe there's some other thing we'll pick up on to prove inflation or something,
Yeah, I mean, there's anomalies in particle physics. There's also there's one big anomaly in cosmology. Actually, there's several, but there's one really big one, which is, as you alluded to, the Hubble tension. And in short, basically what the Hubble tension is, it's a disagreement over how fast space is expanding. And there are two different ways of getting at this in cosmology. One is based on traditional methods where you look out with your telescopes at the universe, you look at distant galaxies, you measure the distances to them, which is actually very difficult and complicated because it's very hard to tell whether a galaxy is big but far away or not so big and close. So this problem of distances is a fundamental challenge in cosmology, that you measure the distances as best you can, you measure how fast they're moving, and you do that using the Doppler shift, so the same effect that makes a siren sound higher pitch when it's moving towards you, or lower pitch when it's moving away. And then you can measure the expansion of space as a function of distance. And that gives you this number called the Hubble constant, which is essentially how fast should a galaxy be moving away from me based on its distance. That's one way of doing it. It's called the direct or local universe method. The other way you can do it is to look at the cosmic microwave background, which is the faded light of the Big Bang, to analyze the patterns that exist in that microwave radiation, and use that to infer the properties of the very early universe, the universe as it was 400,000 years roughly after the Big Bang. And then using that knowledge of the early universe, you can use general relativity and our sort of theory of cosmology to run the clock forward to the present day and predict effectively what the expansion rate should be. And these two numbers, one based on the local current universe and one based on the early universe extrapolated forward, don't agree. And they don't agree now by quite a big amount, by over 5 sigma. And this tension has been simmering away for about a decade now. And it's every time, people have challenged it and said, well, there's probably a mistake in how we measure distances, for example, in the local universe. People have drilled into it and the tensions just got bigger. So it's a really perplexing problem. There are many explanations on the market, but I think what makes why people struggle so much with the Hubble tension is that none of the explanations are really that compelling. So one explanation is that there was a form of dark energy, so some kind of unknown repulsive force that existed in the early universe, but then disappeared conveniently in the late universe, in the universe we live in now. Other ideas that, our theory of gravity, more radical end would be our theory of gravity needs to be revised. Other ideas are actually, it's just that we happen to live in a void in space, so an area in the universe which is underdense, where there's less stuff than there is elsewhere. And that would explain why we see it apparently expanding faster than it ought to be, because we just live in a weird place. So there's all these kinds of ideas around, and no one really knows what the right explanation is yet. But I think of all the anomalies that I talk about in Space Oddities, the Hubble tension is the one that to me looks the most compelling. Now, whether it's going to lead to some fundamental shift in our understanding of the universe, or, or something, it seems unlikely now that it's an experimental mistake. I think that, it's been around for such a long time. I would be quite surprised now if it turns out there's an error, because there's so many different measurements, different techniques. They all pretty much agree. So it's either something fundamental and really exciting. Maybe it is something to do with the fact that we live in a weird bit of the universe and we're just a bit unlucky. One of the interesting things one of the assumptions, or not assumptions, but sort of an assumption in cosmology, is this thing called the Copernican principle, which is the idea that we don't live anywhere special. So our bit of the universe is representative of the universe as a whole, and that the universe is isotropic and homogeneous. So it looks the same in every direction, and it's got the same density and properties in every direction. If that's not true, then it really screws you, because it kind of means it's very hard to figure out the bulk properties of the universe as a whole. Maybe that's the explanation. I mean, I'm not a cosmologist, so I'm not really qualified to pass judgment. But definitely, as a sort of someone who's dug into it as an outsider, I think it's really interesting, and it's not the only anomaly. There's this other weird one called the Sigma 8 anomaly, which is basically the fact that the universe isn't as clumpy as it should be. So there's less structure in the universe than there ought to be. So stuff has collapsed less under gravity than you'd expect based on our cosmological theory. So it seems to suggest that there is something missing from our understanding of the cosmos as a whole. And that's an exciting place to be, because, the last time we had something like this, it led to the discovery of dark energy. And so we could be in for a similar sort of breakthrough in the next few years. But we're going to require more data and more clever theoretical ideas to unravel what's exactly going on, I think.
Yeah. So, I mean, you heard it straight from Harry. If you're into any big ideas like this in physics, which I imagine quite a lot of my listeners have to be, you have to check out Space Oddities. It was such a great book. I devoured it. I got it early and I was like, yay, I couldn't wait. I couldn't wait to rip it apart.
Well, thank you so much. I'm really glad you enjoyed it.
Yeah, it was great. And if you're listening to this as it comes out, the book will be out in a few days, basically. So it comes out March 26th. So thanks again, Harry. I could talk to you probably, for a few centuries, but we'll have to limit it to this for now. Thank you. This was terrific.
It was a real pleasure. Thanks for having me on.
Now it's time for Coherence, the Quantum Executive Summary, where I take a moment to highlight some of the business impacts we discussed today, in case things got too nerdy at times. Let's recap. The Large Hadron Collider, or LHC, is the biggest scientific instrument ever built. Harry Cliff analyzes data for the LHCb experiment, which focuses on a specific type of particle called a beauty quark. The team is investigating beauty quarks and their decay to understand the asymmetry between matter and antimatter, potentially revealing new physics beyond the standard model. When looking for an anomaly that rises to the level of a breakthrough in experiments, you need to detect data that moves away from theory by 5 standard deviations. This 5 sigma standard requires a lot of refined work to ensure no errors have crept in. Running quantum algorithms has many parallels, sure, as we're used to contending with noise or errors all the time. In short, you're looking for 1,000,000 to 1 odds that you're wrong to add weight to the claim you've got the right answer. The LHC generates more data in days than every hard drive on Earth could store, so a lot of complex computation is used. Triggers carefully select which data to record, and then massive horsepower analyzes the results. This amount of data will only grow with upgrades to the machine. I think quantum computing might help manage this in the future. Harry points out some other use cases in physics. The most notable is simulation, which goes back to Feynman's 1981 keynote. In the case of the LHC, simulating collisions can help better identify biases in handling the data from real experiments. The hope is that quantum computers will do a better job simulating and tracking what should happen after a collision. These simulations make it easier to analyze real collision results. There's a group of scientists at CERN looking at other ways of how quantum computing could be applied to high-energy physics. See the show notes for a paper link. Harry's new book, Space Oddities, goes into his LHCb work and some of the other anomalies scientists are looking for. The Hubble tension is one example, where there's a discrepancy in the rate of the universe's expansion. If we extrapolate from the Big Bang and the cosmic microwave background radiation, we expect one rate of expansion. But direct observation of distant galaxies shows a much faster rate. You can learn about that, the alleged fifth force of nature, and many examples of how handling data in science leads to amazing discoveries. Space Oddities is available wherever books are sold starting March 26, 2024. That does it for this episode. Thanks to Harry Cliff for joining to discuss his new book, Space Oddities. And thank you for listening. If you enjoyed the show, please subscribe to Protiviti's The Post-Quantum World and maybe leave a review to help others find us. Be sure to follow me on all socials at Constant Hacker. That's Constant with a K, Hacker. You'll find links there to what we're doing in quantum computing services at Protiviti. You can also DM me questions or suggestions for what you'd like to hear on the show. For more information on our quantum services, check out Protiviti.com or follow Protiviti Tech on Twitter and LinkedIn. Until next time, be kind and stay quantum curious.